Hello everyone, my name is Yonatan, as mentioned, and today I'm going to speak with you about foreign functions interface and how it improved our model serving in production in Outbrain. But before we jump into all of that, I would like to start with a little unrelated story. By a show of hands, who knows what those 4 vehicles have in common? We have here 3 airplanes and this strange-looking car called the Beast. And I didn't expect to see many hands because the surprising answer is that they all have the same engine, the Mark 35 Merlin engine. And the hero of that story is this guy, John Dodd, who decided he wants to put an airplane engine inside a car. He built this car in the 1970s, and he had to build the chassis himself because no regular car could fit such a huge engine, and it reached a very impressive speed at that time of 300 kilometers per hour. And I'm telling you this story not because I'm a huge car fan, but because this project reminds me a lot the project I'm about to show you we had in Outbrain. But before that, let's have a more proper introduction. My name is Yonatan, I'm 30 years old. For the last 10 years, I'm a software developer, and in the last 4 years, I'm working at Outbrain. And in order to understand the project that I'm about to show you, we need to get a little bit of context what is Outbrain and what we are doing. So Outbrain is a recommendation system. We have a widget at the bottom of online articles. And as you can see, we are dealing with huge scale, more than 10 million requests every minute, and we are working with the biggest publisher there, Axel Springer, CNN, DMG Media, and many more. And let's put on Outbrain's hat for a second and try to understand how do we decide which is the best candidate to show at a specific article. And in order to do that, we have a metric we call CTR. And the CTR is shortcut for click-through rate. And I want you to think of the CTR as the probability that the user will click that specific candidate. So in that case, we'll pick the one at the top, obviously, because it has the highest CTR. But if you really think about it, we can't really know in advance what is the CTR, right? And that's where our machine learning model comes into play. And our machine learning model takes in one side all the features about the articles and the features about the candidate, and it chews them all together and spit on the other side the CTR prediction, a prediction to what will be the CTR for that specific candidate on that specific article. And as I mentioned, we are serving a lot of recommendations. We receive dozens of features, our model, and it weighs around 3.5 gigabytes. So this part of our serving system is very heavy, both in CPU and latency terms. And beside that, as I mentioned, we are dealing with 10 million requests a minute, and for each request, we want to evaluate hundreds, maybe thousands of CTR of candidates, which leads to billions of CTR predictions every minute. So a huge, huge scale. And that's why we invented our own Mark 35 Merlin engine, which is called Fwumious Wabbit. And the thing that Fwumious Wabbit knows how to do really, really well is calculate predictions very fast. It's written in Rust, and it's based on another machine learning library called Wabbit. And Wabbit was developed by Yahoo, if some of you know it. And both Fwumious Wabbit and Wabbit are open source, so check them on GitHub. And the fact that this engine was written in Rust posed a whole new problem for us in the engineering, because all our microservices are written in Java, and Fwumious Wabbit is written in Rust. So now we have this amazing engine that, exactly like John Dodd, we can't fit to our current car. And this is how our microservice looks like. And it was pretty obvious that we need another microservice that will be able to propagate all the CTR predictions to all other services. And the first solution we had is with a TCP server. So we took the Fwumious Wabbit binary, and we built a TCP server out of it. And our Java service, which is called Citrus, is the microservice, was communicating via TCP communication, and it was all done on the same container to save some latency, some network latency. And I think that from the very beginning, it was pretty obvious to us that something is not right. This solution had many disadvantages, and from the very beginning, we felt like we took this amazing engine we just built and just tied it to the roof of our car and tried to drive like that. And let's see why. What does it mean to have all this TCP communication? It means that our Java service, Citrus, needs to manage a connection pool to the TCP server. Each request needs a resource, we have to validate that the connection is still active. If it's not active, do the TCP handshake all over again. And after we are done, parse all the TCP sockets. So this solution had many obvious disadvantages. First of all, it complicated our concurrency. In Outbrain, we have our on-prem cloud, and we are very good in having a single application on our container and reaching a CPU utilization of 90, maybe 100% before we spin up another instance. But here we have two applications, and getting to this CPU utilization, very high CPU utilization, was much, much harder. Besides that, the TCP communication itself cost us in latency and in CPU. The TCP handshake and the parsing of the TCP socket, and the TCP handshake was something we did many times because connections were failing and closing, as I said. And I think that the most aching problem is the last one, where we just added a huge point of failure to our system, because now if something goes wrong with the TCP communication, we don't have predictions and we can't really serve this request very well. So another huge disadvantage. And it was very clear to us that if we could avoid the TCP communication, things would be much better, both in latency terms and in CPU terms. But how are we going to do that? How are we going to get rid of this TCP communication? I mean, replacing it with any other communication protocol, the UDP, for instance, will probably result with the same problems and the same issues we have. So that conclusion led us to the only possible better solution, which is doing a simple method call. So instead of a TCP server, we have a simple library, a native library, and all the communication will be via a simple method call, loading the library into our application memory. And you all must think to yourself, if it's that easy, why didn't you do it to begin with? And the answer is that it's not that easy. And Java have many limitations with native code, and for very good reasons. First of all, Java types and C types are very different. In Java, we have classes, where in C or other low-level languages, we have structs. And they look very different in memory, and I think that the string class is a very good example, because in Java, string is an actual class with a lot of methods, and it looks completely different from the string in C, where it's simply an array of characters. So allocating memory in your Java code, a string, and then passing the pointer naively will probably result with a hideous error or heap dump. Besides that, Java is memory managed, where other low-level languages like C and Rust are not, which means that the garbage collector can take the data we allocated for the native code and move it around or even delete it before our native library will get a chance to use that data. And the last problem we have is that we need a way to load this library into our application memory and to invoke it, to invoke functions out of this library. And it's pretty easy when we're using Java. We have the JDK, JRE, the Java class libraries, and all that infrastructure where we are dealing with Java libraries. But this is not a Java library. This is a native library compiled from Rust. And that's where Project Panama came to the rescue. And I will mention here that Project Panama gave us the foreign function interface and the foreign memory API that I will go deeply into. But there were older solutions, the JNI and the JNA. They are both not recommended anymore by the JDK. And we had some really bad experience with them as well. So I would probably really recommend you to use the foreign function interface and foreign memory API if you have the same issue. And foreign function interface and memory API was incubated in JDK 17. Since then, in JDK 19, it went to first preview, second preview in JDK 20, and third preview in JDK 21. And now, finally, in JDK 22, it's a closed feature. So I would recommend you to use JDK 22 if you are going to use this feature. Although if you want the long-time support, JDK 21 is also good. It has almost no difference. And what are the components we are going to look at? So the foreign memory API and the foreign function interface, obviously. But I want to mention another very important component, which is the JExtract tool. And the JExtract tool will do automatically for you all the boilerplate code that I'm about to show you. So in order to do those native codes, we will need to generate some code. We'll need memory layouts and method handle. And the JExtract tool can do that for you by feeding the headers of the libraries you have. And it will create a lot of the code for you. And before we jump to the first component, I would like us to take a look at the Rust code we are about to run, and more specifically at the signature of this function. So we have here the pub unsafe extern C, which is simply telling the compiler to compile it with C bindings. And we have this function called fwPredict that receives a pointer to the predictor. The predictor is our model. And an array of characters, which is a string, with all the features we are going to feed the model. The return type will be a float, which will represent this predicted CTR, obviously. And now to our first component, the Foreign Memory Access API. And this component is responsible for solving the first two problems we had, the difference between structs and classes and the garbage collector problem. And I would like to start with the garbage collector problem. And the approach that the developers of Project Panama decided to take here is to put all the memory we are going to pass to the native library in the off-heap memory. And the amazing thing about the off-heap memory in our Java process is that it's not managed by the garbage collector, so problem solved, right? Well, not really, because now we as Java developers need to do something we are not used to. We need to deallocate memory, and more than that, we need a way to allocate and deallocate memory in the off-heap memory, which is something that currently it's not easy to do in JDK. And that's why the developers of Project Panama created the arena, which will allow us to do all this, and we'll take a look at a real production code from Outbrain. So this is the Java function that is going to do the prediction. It receives a byte array with all the contextual features and a list of byte arrays of all the candidates. And the first thing we are doing is we are initializing two variables, the predictions and the max candidate byte size. The max candidate byte size we just need in order to create the buffer. And now the first really important class we are going to see here is the arena. And with this instance of the arena, with arena open confined, we are going to do the allocation in the off-heap memory and the deallocation. So the allocation is pretty easy. With this instance of the arena, we can use session.allocate, define the size, and we get a memory segment, another class out of the Foreign Memory API, which will represent a memory in the off-heap memory. Now, once we are out of this try scope, if you can see here, this memory segment we just created will be automatically deallocated thanks to the fact that the arena implements the auto-closable. Now that we have the buffer, we can, with memory segment.copy, copy all the contextual data. And for each candidate, we are going to do the same, copy all the specific candidate features. We set the last byte to be a 0 byte, and we simply send the buffer we just created to our native fwPredict. And I will go into this native fwPredict and how exactly we are doing that. But before that, I want you to take a look at these little curly braces at the end. Once we are out of this scope, the memory segment we just allocated will be automatically deallocated because the arena will run its close function. And that's a very nice and implicit way for us with arena to deallocate memory. And once we have all the predictions, we return the predictions. And now, before we are going to go to how this native fwPredict works, I want us to solve the second problem that I mentioned, the difference between structs and classes. So we, in Outbrain, didn't really need to solve this problem because byte array looks the same in C and Java. But I created here a dummy example because there is a solution in the Foreign Memory API, and it's a very nice one. And the solution is memory layout. And here I created an example of memory layout of a rectangle, and I have my native area calculation, which is very efficient. And using the memory layout.struct layout, I'm specifying the value layouts, both the width and the height. They are both double. And using that layout, I can create a var handle. And the var handle is another amazing addition, because using this var handle, I will be able to set the values I want for the height and the width without calculating the offsets on my own. All I will need to do is create an arena, obviously, first. And now allocate my rectangle that I want to pass to my native function. If you will see here, we are not allocating with the size of the byte array. We're simply passing the rect layout, the memory layout we created, and it will know how to calculate it on its own, which is pretty amazing. And now, using the instance of the memory segment we just created and the width handle, we can set the values very easily with the width handle.set, specifying the instance of the memory segment and the value we want, and we didn't need to do any of the calculation ourselves. And it's even more powerful when your code changes, because let's say I'm now calculating an area of a tensor. All I need to do is add another variable, the depth, create another var handle, and now it will automatically allocate the correct size because I passed the tensor layout, and I just set another value for the depth. And that's all I need to do. And now to the second component, the foreign function interface. And this one will solve us the third problem, which is loading the library into our application memory and getting a function, a way to invoke that function from the native library. And if you remember, we left off here in this native fwpredict where we passed the buffer we just created. And native fwpredict is a bit anticlimactic. It's another private Java function. But the real place where the call to the native function happens is in this try clause. And the fwpredict.invokeExec is how we are doing the actual call. And here we send the predictor and the buffer, we receive a float. It looks much more like the signature of the Rust function we just saw. But that's all, right? It's a bit too easy. That's all we need to do? Well, not really. The heavy lifting is not here. It's not where we are calling the method. The heavy lifting happens where we create this fwpredict, this method handle. And method handle is not a new class. It exists in the JDK, I think, from JDK 7. But the class that will create the method handle for us is the linker. And more specifically, in our case, the native linker. And it will create it in the constructor of our class. As you can see here, our constructor receives the path to the library, to the native library we are about to invoke. And the first thing we are doing is creating an arena, because this library is going to live in our application memory. And we don't want the garbage collector to move it around or deal with it. So everything will be allocated in the off-heap memory. And with this arena and the library path, we can use the symbol lookup. Symbol lookup is one of the classes out of the foreign function interface. And the symbol lookup, using the .library lookup, where we pass the path and the arena, will get us the symbol lookup instance, and it will do two things. First of all, it will load our library into our application memory. And the second important thing it will do is it will map all the functions this library contains, so we will be able to get a memory segment of the specific function we want using the symbol lookup.find, using this instance we created, .find, and passing the name of the function we want to invoke. Now, with this memory segment and the function descriptor, which I will go in a minute, we can use the linker that we created at the second line, linker.downcall handle, pass the memory segment we just created and the function descriptor, and we'll get the method handle. And I still owe you an explanation of the function descriptor. And this is a very cool addition we got from the developers of Project Panama. And if you will think about it, when we are dealing with Java libraries, we have the compiler to make sure we are passing the correct parameters and getting the correct return type. But this is not the case. We are dealing with native library, and everything happens in runtime. So we will not get this compiler safety net. And instead of that, if we pass the wrong parameter, we'll probably get a hideous heap dump. So using this function descriptor, the developers of Project Panama gave us a way to describe what is the type we expect the function we just trying to load from the native library. What is the signature we expect to have? So in this case, we expect it to return a float and get to 2 pointers. And using that, if we, for some reason, function descriptor gets a Boolean and 2 pointers, and not only 2 pointers, it will say something is wrong with the function descriptor instead of sending up some hideous heap dump. And I guess that by this point of the session, most of you feel like that. And it's totally fine. You didn't need to get all the bits and bytes of how the foreign function interface works and foreign memory API works. When you will need to do it in your own project, you will do the deep dive yourself. I hope you got the broader picture, the problems that needed to be solved when you are dealing with native libraries, and the way that the developers of Project Panama solved them. And now to the most interesting question. So we removed the TCP communication. We did the simple method call. What was the impact? How much did it save Outbrain? And the impact was huge. It reduced our CPU cores by about 3,000. It reduced our RAM memory by about 3 terabytes. It reduced the tail latency in 30 to 60%, and the average latency in 20 to 35%, which is amazing results. And I know that those parameters can be a bit ambiguous, so I converted them to a parameter we all know and love, which is money. And we are not working with AWS. As I say, we have our own on-prem cloud, but I took the instances that are the closest to the one we were using, and this fix alone, this change alone, saved us around 750 of those, multiplying by 110, which is the monthly cost, is almost $90,000 a month, which is amazing. And I would like to end the session with a little confession. When I created this session, I thought this is a very interesting project we had in Outbrain that was very successful and used the really cutting-edge technology in the JDK, but I was a bit afraid that most of you will never need it because it felt to me a very unique problem, calling a native library from your Java code. So I did some search online, and I was really surprised on how broad this problem, and here are just some of the fields where this solution can be super relevant. So anything related to the security, a lot of the libraries are written in low-level languages, IoT, robotics, medical industry, a lot of the libraries to a specific medical instrument is written in low-level languages. And like in our case, machine learning. And Fwumious Wabbit and Wabbit are not the only libraries only available in a low-level language compiled to C. TensorFlow is also an example for such a library, and CUDNN. So a much broader problem than I thought. And that's it. Thank you very much. If you want to contact me, this is my Facebook, my LinkedIn.